Hi everyone, so this is the last video in the photoelectric effect concept, and I just want to do an example to show you how we can use Einstein's equation. Remember that that's the kinetic energy of the electron equals h nu minus h nu naught to calculate different things here about the conditions of the photoelectric effect. So in this particular case, we're given a question here where it says the work function for chromium metal is 652.7 kilojoules per mole, and then you're being asked to find the energy needed to remove an electron from one atom of chromium, the minimum energy a photon must have to ionize chromium, and then lastly the maximum wavelength of light that can ionize chromium. Okay, so let's go and work out these problems. So it says first off that you have a work function and it has a value of 652.7 kilojoules per mole. Okay, if you go back to that Einstein equation, remember kinetic energy is equal to h nu, which is the energy of the incoming light, minus h nu naught. And of course this component here is what our work function, I'm sorry, not just phi, our work function is, okay? Is that part of it. So what we want to know now is the first question is asking how much energy does it take to remove an electron from one atom, okay? Energy to remove one electron from one chromium atom, okay? Now if you think about this, this is really asking you about the work function itself, right? I mean, it's asking you the energy needed to remove one electron. Remember, the work function is also the ionization energy, the first ionization energy, which is the energy needed to remove the first electron from an atom. So that's really, it's just asking you for this number, but the difference is that it's asking you that number in terms of one electron. The information you're given is in 1 mole of electrons. So if you think about the work function here, 652.7 kilojoules per mole of what? Really per mole of electron, because the work function is defined as the energy to remove electrons, right? So if that's the case, the work function then for 1 electron would just be 652.7 kilojoules. This is per mole of electron, right? Times, of course, our conversion factor, which is 1 mole of electron has to contain 6.02 Avogadro's number of electron, right? So that would be your answer there. And I'm going to give my answer in terms of joules instead of kilojoules. I'm going to convert everything to joules and then put out my answer. If you run this on the calculator, you get 1.08 times 10 to the minus 18 joules per electron. Okay, so remember that now this is the work function per electron. Okay, so you just have to be a little careful there when you read that question again. If I move back to the question, if you read that question again, it says the energy to remove 1 electron. So that's why what we end up calculating is the energy per electron from the energy of 1 mole of electron. Now if you look at the second question, it says the minimum energy a photon must have to ionize chromium. Okay, so let's go back here. Okay, so we have this equation, right? We have Einstein's equation, which looks like this. And what it says here is that the kinetic energy of the electron will be the difference between the energy of a photon that hits the surface of the metal minus the work function. Now, if the work function has this value right here, what is the minimum energy a photon must have in order to get the electron off that metal? Well, the minimum energy, if you think about it, right? Minimum energy of photon to get the electron off the metal must be equal to the work function, right? That's the only logical explanation. If I want to get rid of get that electron off the metal, I have to have the energy at least equal. This energy, h nu, has to be at least equal to that in order for the electron to come off the metal. Now, if I have energy more than that, then the rest of that excess energy is going to be converted to kinetic energy of the electron. Okay? So in other words, the answer to part B is really the same. The minimum energy of the photon should also be 1.08 times 10 to the minus 18 joules. Okay? Again, per electron. Now you might wonder, well, why am I asking the same question twice? Well, I'm not necessarily asking the same question. I'm asking the question two ways. The value of the answer happens to be the same, but you're not asking that same question. You're really, the question is really trying to get you to understand that there's a difference between the energy, the ionization energy, which is the energy needed to remove this first electron, and then the photon that's reactant. So one is the energy that's holding the electron in the nucleus, in the atom, I'm sorry, by the nucleus. And then the second one is the energy that the photon must have in order to knock out that electron from the atom. Okay? Now this last question here says maximum wavelength in nanometer of light that can ionize chromium atom. Okay, let's go back here again. We just gave this answer earlier, which is the minimum energy that a photon must have in order for it to be able to take out your electron from chromium is this value right here, 1.08 times 10 to the minus 18 joules. Okay, this is per photon, right? Now, we know that the question here is asking about wavelength. Now, we know that this energy, the energy of photon, is given by Planck's equation, which is h nu. But we're not being asked frequency, we're being asked wavelength. Wavelength and frequency of light are related by the speed of light, and in fact it's equal to hc over lambda. Okay, now let's think about this term first, lambda max, right? It's asking you about the maximum wavelength. We go back to that question. So now I want to talk to you a little bit about doing some reasoning here. If this quantity that we just calculated is the minimum energy of the photon, that means that it's equal to h nu. H is a constant. That means that the minimum energy must come out because there is a minimum frequency that we must have in order to get this number. So the energy of the photon could be this or higher, and as a result the photon must have a frequency of at least this or higher. And in fact, that's been our description of the photoelectric effect. We talk about this quantity called nu naught, right, which is a threshold frequency. So that's really what that threshold frequency is. Okay, but this question is not asking you about the frequency, it's asking about the wavelength. So if you write the equation in the form of wavelength, you have hc over lambda. You see that lambda, wavelength, and nu, frequency, have an inverse relationship. So the smaller frequency is, the larger lambda is. As a result, if I'm talking about minimum frequency, that means I'm also talking about maximum wavelength. Because if I go bigger than this wavelength, the energy is below this number. If the energy is below this number, no electron is going to come off the surface of the metal. Okay, so hopefully you understand that reasoning. Now, if you understand that, then the next part of it is just calculating. So I'm going to rewrite the equation to solve for lambda max, which is just going to be hc 6.626 times 10 to the minus 34 joules second, right? And then multiply this by speed of light, 3 times 10 to the 8 meter per second, and then divide this by the energy that we're given there, which is 1.08 times 10 to the minus 18 joules. Okay, now you notice again, I want to emphasize this, what I'm using here is I'm using the value that I calculated for one photon. I'm not using the value that I got earlier that was given to me in mole of electrons, because that would also be the energy of 1 mole of photon, right? And the reason for that is because when I'm talking about hc here, I'm talking about the energy of 1 photon. When I'm talking about h nu, I'm talking about the energy of 1 photon, because remember, Planck's equation has n in front of it. If I want 1 mole, then this n would be Avogadro's number, but in this case we're just given h nu. That means that it's just n must be equal to 1 in this case. That's why I'm using the energy for 1 photon, which is a very small number. Okay, if you carry out this calculation, first off, I just want to point out the units. This cancel, and per second and second cancel, leaving you with just meter, which is the unit of length and wavelength. And what you get is a value of 1.83 times 10 to the minus 7 meter. Now, for these type of experiments, a lot of times wavelength, because we're usually are accustomed to expressing this in terms of the visible wavelength range, and remember that that's between 400 to 700 nanometers. A lot of times the units would be expressed in nanometers as well. So for this answer, we would actually write that the answer would be 183 nanometers. As it happens in the question itself, it's asking you to express this in nanometers. But I just want to make sure that you're used to this idea that when you're talking about lambda wavelength of light, especially visible light, usually it's expressed as nanometers. Okay, so you want to be comfortable being able to interconvert between meters to nanometers. Okay, we're going to do some more problems in class on photoelectric effect, but I hope this gives you the idea of how to do these type of calculations.